Yeah, as Darren mentioned, I'm Jake. I'm CEO and one of the co-founders of Authzed. At Authzed, we are building a commercialized implementation of Google's Zanzibar paper. So the Zanzibar paper is something that we know and love very well. The Zanzibar paper was released just about 2 years ago now, in the summer of 2019. And the lead author was Roming Pang, and then there were about 8 or 9 other authors. Okay, uh, so just a quick introduction of myself. As mentioned, I'm the CEO and co-founder of Authzed, but I've also worked at a lot of really other cool places on a lot of other really cool things. So before founding Authzed, I worked on a project called Quay that got bought by Red Hat. Red Hat got bought by IBM, et cetera, et cetera. I was at Google pre-Zanzibar. I was at Amazon working on the e-commerce platform. And yeah, all in, I've been building and developing developer tools and distributed systems for over 15 years. And tonight, I hope to impart on you that Zanzibar is a good enough paper to drop everything and start a new business. So that's just how impacted I was by the paper and the contents of the paper, and I'd like to share with you why. Before we get started on the actual technical solution known as Zanzibar, I want to talk a little bit about the problem. So why did Google even decide to stop doing Zanzibar? Like many other companies, Zanzibar is not Google's first authorization system. So they started with an ad hoc system, like many of you. An ad hoc system can be any authorization model. It can be RBAC, it can be ABAC, it can be relationship based. And usually the way that's implemented is by just storing some relationships in your database and then interpreting those relationships in source code. It can be very performant because you can tailor the whole thing to your use case very well, very specifically. Then they moved on to a library-based implementation. This is trying to get to better reusability and higher consistency. So when a library-based implementation, there was one shared piece of source code inside Google that all services would compile into their service binaries, and then they would have a consistent way of checking authorization. The library also suffers from some problems, but has some nice sides. So the library can, again, represent as many different authorization models as you want. It does give you a consistent way to interpret relationships, but they're often language specific. So usually you will have a library and then either a re-implementation of that library for each language or bindings for each language. Some common examples of library-based authorization systems today are like Ruby's can, OSO, Caspin, Django has an RBAC built in, those kinds of things. But finally, Google landed on their most recent iteration, at least that we know of authorization, which is a network service called Zanzibar. And a network service is really well suited if you have a suite of applications that are all talking to the same permissions model and the same permissions data. And it gives you language portability. So all you have to do is create a new client library for compute permissions in. So I'm going to start with some basic requirements for an authorization service that could be used at any enterprise, or some requirements that would be applicable to most enterprises. So if you are going to do an application suite or more than one application in your permission system, you probably want it to be multi-model. In Google's example, they use the same service to back things like Google Drive, which is sharing based or like point-to-point sharing based, and things like YouTube, which are one-to-many, or Google Cloud IAM, which is more of a RBAC system. You want it to work across applications uniformly. So a great example of this is when you're about to send an email with a link to a Google Doc that the recipient doesn't have access to, Gmail will warn you. And the way it can do that is because it actually talks to Zanzibar ahead of time and says, it knows the identity of the recipient, and it says, does this recipient have access to this doc? And if not, it throws up the warning. You can also build higher level visibility of your permissions on top of a network service. So once all of the data is concentrated, you can start answering questions like who has access to what, is anybody over permission, those kinds of things. And then any permission system, you're going to want it to be correct foremost, because you don't want to give out wrong answers, because then the whole game is lost if you start giving people access to things that they shouldn't have access to. And ideally, it will also be consistent. And I'll touch upon consistency quite a bit later on in the talk. But Google being Google, they also have some googly requirements. So Google has billions of customers. There aren't that many companies that can say that. Their authorization service, as we'll talk about later, also performs millions of requests per second across trillions of objects that Google is managing. And it has to do all of this quickly as to not impact the user experience too much, reliably, and from anywhere in the world. So Google has users on all 7 continents. I want to talk about reliability for a second. So a lot of services think that like 99.5% uptime is a really great reliability metric. If you've read the SRE book, you know that Google calculates uptime based on as successful requests divided by all requests. So at millions of requests per second, even 99.5% uptime is over 4 billion failures per day at Google scale. So this is something that they really have to focus on and do really well. So that takes us to the Zanzibar paper itself, the paper that started it all. Like I said, this came out in the summer of 2019. And all of the data that we'll talk about today is as of summer of 2019. So some of it may have been updated. There may be things that we don't know about occurring. I'm confident there are things that we don't know about occurring within the walls of Google that aren't encompassed in the paper. So the sections I'm going to cover today are sections 2, 3, and 4. Section 2 covers the model and API. Section 3 is a lot of implementation details and architecture diagrams. And section 4 actually talks about how the service has been performing in production at Google. So without further ado, we'll jump into the model, language, and API. Before we can talk about the API, though, first we have to talk about the lexicon, the words that Zanzibar uses to talk about things. So there are 5 major, I'll call them nouns or entities that we want to talk about with Zanzibar. There's user, object, relation tuples, and namespaces. A user represents a natural person or a service account inside Google. And all users inside Google are assigned a globally unique integer ID by a service called Gaia. Gaia stands for Google Accounts and ID Administration, and it is the source of truth for anything authentication related inside Google. So for example, myself, that is a really long integer ID that may or may not represent me inside of Google. If you know of any hacks that rely on that ID, please don't exploit them. So then we have objects. Objects represent non-user entities that participate in permissions decisions. There are unique identifiers prefixed with an object type. So I have an example of a folder called secret plans, and I have a doc called secret doc ID. But other things that could be objects would be like groups, videos, roles, if you're implementing RBAC on top of Zanzibar, organizations, those kinds of things. Then we have relations. So relations are the way that one object can be related to another object or even directly to a user. And some examples of relations are you can be a member of a group, you can be an editor of a document, you can be an uploader of a video. And those relationships that you have to that piece of data may confer specific permissions or authorization things upon you. So what happens when we combine objects, users, and relations together? We get relation tuples. Relation tuples are individual facts or an individual datum which expresses a single relationship inside the Zanzibar service. They have this super terse, easy to read a lot of syntax, but not super easy to understand. So I'm going to walk through a few examples of the relation tuples. So in this example, this relation tuple says that user 3 is an owner of a document, and that document has identifier 123. That 123 is obviously just made up. That could be a UUID, it could be a database row number, it could be really anything. And the number 3 is the integer representation of that user within. But objects can relate to more than just users. They can also relate to other objects. So in this example, we have an object that says that the group security is a direct member of the group engineer. You'll notice there's an ellipsis in there. That ellipsis is just a magic string constant, which means that we're talking about the group as a whole, the group security as a whole, and not a sub-relation of the group security. And the reason we need that is because objects can also relate to other objects' relations. So in this example, users or other objects having the member relation to the leadership group also now have the manager relation to the engineering. I'm going to pause on that one for just a second because it is sort of interesting and also the most complicated relation tuple format inside of Zanzibar. So yeah, relation tuples represent relations, and they have a very terse and hard to understand syntax, but basically it's an easy to understand concept. And that brings me to namespaces. So namespaces actually define the object types, those prefixes that you can use when you're building relation tuples, and the relationships that they can have to other objects or users, as well as instructions on how to reinterpret relations to infer other relations. Here's kind of an eye test example of that. This is a namespace example lifted straight out of the Authzed playground, and it defines an object type called document. And then it has a direct relation called writer. And then it has a computed relation called reader. And the computed relation for reader says, I want you to consider everybody who has the direct relation of reader and also users who have the relation writer. So what we're basically saying here is that all writers should be considered readers. Okay. And when we put all of this together, these relationships and computation and all this stuff, what are we actually doing? We're building a directed acyclic graph, of course. So in this example, this is similar to the one we just saw. But in this example, we have an owner relation instead of writer. And then we have an indirect relation that actually goes through another relationship called organization and brings in the administrators of that organization and also considers them as owners. And those owners and admins together are also considered readers. And then you can have direct readers. So just an example of how to read this. Fred is a direct reader of some document, and Jill is a direct owner and a transitive reader of the document. And Hannah is an admin of the org. And Hannah is also a transitive owner and a transitive reader of the document. So now that we've got the terms out of the way, let's talk about the API. So the API has your basic CRUD operations for relation tuples. So these are creating, reading, modifying, and deleting those relation tuples to build up those relationships over time. There's an API to watch changes that are occurring on those relation tuples. This is really useful for pieces of infrastructure to understand what's happening. For example, you could have a cache that was watching mutations, or you could also have like audit logs that are watching mutations. There's an expand API, and what an expand API does is it goes to that directed acyclic graph and it flattens it and basically turns it into a tree and gives you the entire tree contents so that you could choose to interpret those relationships how you wanted. And finally, and probably the most important API, is there's the check permission API. The check permission API will answer the question, does user X have access to object Y? And then there's also a way to answer that with bounded standards. And I'll go into that a little bit. So just as an example of how we turn this directed acyclic graph into an authorization check, I'm going to walk through checking if user 6, who in this case is Jill, has the reader relation on the document some document. So what we do is we basically follow the arrows in the directed acyclic graph and try to find if there's a route between the document in question and the user that we're trying to test. So in this case, we are able to find a path between Jill and the document. So Jill is considered as having the reader relation on the document. And you could consider, or you could understand how this could become a permission by saying that if you have the reader relation, you are allowed to read the document. And the last thing in the API that I want to talk about are Zookies. It doesn't say this in the paper, but Zookies are presumably a portmanteau of Zanzibar cookies. And they represent a specific point in time. When these Zookies are passed back to the service, they force check requests to use information in the system that is at least as fresh as the point in time represented in the Zookie. It being at least as fresh is a way to set an upper bound on the amount of staleness that you're willing to accept as the caller. They are opaque to the caller, so similar to a lot of web cookies, you don't really know what's stored in them as a user. And you should actually have them live with the data so that they are updated and replicated when the data is, and you can pass them back when you want to do permissions operations against the data. And they solve the new enemy problem. I'm not going to assume that you all know what the new enemy problem is, so we'll define it. The new enemy problem is when you apply old ACLs to new content, or when you evaluate changes to ACLs out of order. I will run through an example of the former. So in this example, we have two users. We have the user Lex and the user Kara. Lex has the reader permission or the reader relation on plans, and Kara is an administrator of the plans document. So at time t1, Kara removes Lex's reader permission. At time t2, Kara uses her admin permission to mutate the document and add secrets to the plans. This makes Lex an enemy because Lex should not know about the secrets that are added to the plans document. At time 3, Lex attempts to read. Because this is a distributed system, potentially the data used to compute the permissions response could be stale. And we could use data from before time t1. For example, at time t0, when Lex had reader permission. This will allow Lex to see the secret plans that he shouldn't be able to see because his permissions were revoked before the secrets were added. And since Lex is a villain, chaos obviously ensues. So how would this change if we use Zookies? Similarly, at time t1, Kara will remove Lex's reader permission. At time t2, Kara will use her admin permission to add secrets to the plans, and she gets back one of these Zanzibar cookies that codifies that future requests should happen after time t2. They should consider only data that was created after time t2. Now, when Lex attempts to read, the t2 Zookie is sent back with the access request when Lex attempts to read the document. Zanzibar determines that it needs to use information from after Lex's reader permission was removed. And then now Lex is denied. And we've saved the day. So the crisis is averted. Our new enemy remains unable to read the secrets that we've added. Okay, that sums up the API. Now let's go into the really fun part, the architecture and implementation. The paper segments these different portions into sections as if they were developed independently. Knowing the way that Google operates, I have to assume that they were all co-developed. So you'll see a lot of things in the API that were influenced by the architecture and things in the architecture that were influenced by the performance, etc. So we're going to start with another eye test. This is the architecture diagram directly from the Zanzibar paper. Data persistence is in green. Services, like things that will run on servers, are in yellow, and the clients themselves are in blue. The major things to take away from this architecture diagram is that the majority of relation tuple persistence is done in Spanner. As you can see by all of the servers in kind of the middle left having arrows to one another, we can assume that there's going to be some kind of communication or gossiping between these servers. And then over on the right side, we have a system called Leopard, which does some denormalization of group membership. And I'll talk about that a little bit more. So as we noted, all of the relation tuple persistence is done in Spanner. So Spanner is Google's globally distributed, consistent relational database. In this particular case, we have a globally distributed permission service. And so it makes sense that we would pick a globally distributed database to base it upon. One really important thing to note about Spanner is that it relies on atomic clocks in Google data centers to make sure that operations are ordered in a consistent fashion. I highly encourage everybody to check out the Spanner paper if you haven't read it yet. It's another really interesting paper coming out of Google talking about distributed systems and how they made really practical choices to accomplish something very difficult. But one thing that did come out of the Spanner paper are some performance numbers. So this chart is the F1 perceived operation latencies according to, or put in other terms, how the service F1 at Google, which is an ad service, perceived the latencies of Spanner. In the first column, we have the mean latency for reads, 8.7 milliseconds. Very respectable. You could definitely see building a service on top of a data store that responded in 8.7 milliseconds globally without any further complications. However, the standard deviation of reads is actually several orders of magnitude higher than the mean latency. If you know anything about statistics and normal distributions, this is like kind of crazy. But because of the way Spanner replicates data, it's sort of unavoidable. So when we have this super really long tail latency characteristics, we have to figure out what to do when we hit that kind of worst case. So the Zanzibar strategy is to make as few calls to Spanner as humanly possible. And there's a variety of strategies that Zanzibar uses to reduce the amount of round trips to Spanner. So the first thing that we do is we can break down the main problem into parallel subproblems. So rather than putting a lot of load on one Spanner node that might be overloaded, we can try and talk to a bunch in parallel. At the service level, in Zanzibar, we can actually cache every problem and subproblem to make sure that we're not recomputing data and making more round trips to Spanner if we don't have to. Once we've got the cache in place, we want to try and reuse it as much as possible. There's some really great strategies for increasing cache hit rate, and we'll talk about a few of them in just a second. We want to deduplicate all of our requests. So if one server gets the exact same request and they would be running concurrently, Zanzibar will actually deduplicate those requests and just serve the same answer back to both callers without computing the data 2 times. We want to batch reads to our data store. If you're familiar with the data loader pattern, we can basically make it so that there's nothing else that we can possibly accomplish without going to Spanner. And then we can make as many reads to Spanner at the same time as possible in a single round trip. And the last kind of performance hack that's in the Zanzibar paper is the leopard cache. And the leopard cache pre-computes the transitive closure of group membership within Zanzibar. So groups are highly recursive and they can't be computed in parallel. So for example, a group can be a member of another group, but you won't know that before you resolve the members of the first group. And only then serially do you resolve the members of the second. So this can lead to a lot of recursive, we call it recursive pointer chasing. That's what the paper calls it. So now I'm going to walk through an example of breaking down a main problem into a subproblem or some subproblems. So going back to our original example of trying to determine if Jill has the reader relation on some document, we can actually break this down into 3 subproblems. So the first is figuring out if Jill is a direct reader on some document. If so, problem solved. We know the answer. Next, we can have a different subproblem where we compute directly, is Jill an owner? And one interesting thing to note is the result of computing whether Jill is an owner could also be used to answer Zanzibar requests for, is Jill an owner of this document? So in that way, we can reuse the cache even for the subproblem answer. And finally, the third subproblem is finding out whether Jill is an admin of the organization that the document belongs to. So now we've got 3 subproblems, and these are, as specified in the namespace configuration, these answers to these subproblems are unioned together, which means that as soon as we know the answer, as soon as we know an affirmative answer to one of the subproblems, we can return the answer to the entire top level. So in this case, as soon as we know that Jill is an owner of the document, we can actually discard, not wait for, or choose to wait for and cache the responses for the other requests that we've made in parallel. Earlier, I alluded to improving cache hit rate. This is super important to getting the kind of performance and uptime requirements that Zanzibar needs. And the way we try to improve the cache hit rate are to pick subnodes, because remember, every subnode is running an independent cache that has answers to problems and subproblems. So we want to try and pick subnodes that are likely to already have the answers. We can also leverage the fact that immutable decisions, or decisions are immutable at a given timestamp. So that means if we went back to our example and we computed that Lex did have read access at T0, we can always give that answer back without recomputing it. Similarly, if Lex did not have access at T2, we can also give that answer without recomputing it. So we can just skip the whole union, subproblem, everything, just give the answer. We can try to pick timestamps that already have their data replicated globally in Spanner. So the way Spanner works is as soon as you write data, that data is not yet available globally, but if one tries to ask for it from a different region that it hasn't yet been replicated in, Spanner will actually go and ask for the data from the region where the data is present. So that's where we start to see some of those really high latency high tal call latencies. We can also pick timestamps that can be shared. And I have an example of this in a minute as well. But basically, the more often we ask for a piece of data with a specific timestamp, the higher the likelihood that that data will be cached in one or more of the nodes that we talked to. So first, let's talk about distributing the subproblems. So Google has an internal system called Slicer. Slicer is a consistent hash that is also tied to Google's server infrastructure. And what it does is it allows them to bring up a consistent hash with shards and basically eliminate and alleviate hotspots on those shards and bring up more cache fragments and add them to the consistent hash automatically. I don't have time to cover consistent hashes in this talk, but I definitely encourage everybody to also go read the Slicer paper and just read about consistent hashes in general, because they're incredibly cool and they're one of the primary tools that we have in our tool belt for building scalable distributed systems. There is an implementation of a consistent hash that is informed by Slicer called ring pop that's coming out of Uber. But because it's not tied to a particular infrastructure, it doesn't have a lot of the optimizations that Slicer talks about. And the second thing that we can do, which all kind of revolve around picking the proper timestamp at which to compute data, are the other things that we can do to improve our cache hit. So here I have an example for how to pick a timestamp. So this is just a timeline of events. It reads from left to right, like most timelines you've probably seen. So at a very early time, an ACK was updated. An example of this is Kara removing Lex's reader permission. A little bit later, Kara modifies the document and is issued a Zookie. And then at some time in the future, a request is made with the Zookie. Because we're building on top of Spanner, and Spanner has replication delay for the data, there's also sort of a pointer, which is a reliable timestamp before which you can assume Spanner will have the data replicated globally. And that's represented by that by this middle box here chart. So now we're going to talk about how we pick a timestamp given these specific events occurring in this specific. So first, we can talk about the valid evaluation. Because the request was made with a Zookie, we can use any timestamp that has occurred after the one that's encoded in the Zookie. You'll notice that the red line actually goes past the request time. It's totally valid in Zanzibar to use a future timestamp if you want to make sure that you have absolutely all of the latest data before you make your decision. But we can do a little bit better than just picking from this red line. If we pick a timestamp from data that's also replicated or that's already replicated globally, we can eliminate most of those high latency tal call situations that we saw in the F1 table about Spanner performance. So in this case, we're going to try and pick a timestamp from already globally replicated data, but still fresh enough according to the Zookie. And you'll remember that earlier I talked about picking timestamps that are likely to be shared. One way we can accomplish this is by quantizing our timestamps and making them, essentially rounding them, and making it so that we're likely to pick the exact same timestamp in a distributed fashion from a variety of different servers making these authorization evaluations. One thing to note is that the quantization that you pick directly drives hit rate, but it's not as obvious as just making the quantization as large as possible, because the wider you make the gaps between those quantization times, the less likely you are to actually be able to pick an old enough timestamp that's also newer than the second. So it's kind of a parameter that you want to play with and look at your cache hit ratio for each type of data that you're dealing with, or each access pattern. So the Zanzibar paper didn't actually publish cache hit rates, but we're lucky that there's another implementation of Zanzibar called Airbnb's Himeji that did publish their cache hit rates. And they're seeing a 98% cache hit rate using some of the same distributed systems primitives or the distributed systems techniques that are described in the Zanzibar. 98% is a really good cache hit ratio. So that is how Zanzibar was implemented and some of the distributed systems choices that they made. Now let's talk about how they did. Right? This is obviously a huge service at Google, taking a huge amount of traffic. So the first thing to note is that on the latency front, Zanzibar does really well. So with a mean latency of 3 milliseconds, so the 50th percentile, I guess the median latency of 3 milliseconds, and a 99th percentile latency of 15 milliseconds, this is a fast service. You can safely call out to this service if it's in an interactive user flow. Right? So if somebody makes an API request, it's okay to call out to Zanzibar because you're likely to get your answer back very fast. Next, how does it scale? It's a distributed system, so we want it to scale really well. So in their own words, Zanzibar serves more than 10 million client queries per second, QPS, and it does that across 10,000 servers. I've built some high-scale services, but 10 million QPS is still a really impressive number. And we've kind of come to expect 10,000 servers on Google, which is mind-boggling in and of itself. And how about uptime? And again, in their own words, Zanzibar's availability over the past 3 years has remained above 5 nines. If 5 nines sounds familiar to you, that's also the uptime target that the plain old telephone system used, or telephony systems use for their uptime requirements. So these are things that Google wants to just work. If we take our same 10 million requests per second and we use 5 nines of uptime instead of 99.5, you can see how drastically that will reduce the 4 billion failures per day that we expect at 99.5. Okay. This brings me to the last section of my talk, the various implementations and their deviations. So there's actually 3 kinds of Zanzibar that I like to think about. There's Zanzibar, the service at Google, which has presumably moved on 2+ years since the paper was published. So it is not the Zanzibar that we all know from the second type of Zanzibar, which is Zanzibar the paper. And then there's what I like to call Zanzibar the meme, which is that everybody is doing Zanzibar right now. So you'll hear about it more and more as time goes on. But not all, I'll just say that not all Zanzibars are created equal. So for each implementation that we're going to go over, I'm going to show one of these like example scorecards. And I'm going to break the scorecard down into 5 sections. So paper faithfulness, right? How much of this is Zanzibar the meme versus Zanzibar the paper? Scalability. How much do we know about how well this individual implementation will scale? Which cap compromise did it take? If you're familiar with distributed systems, you're probably familiar with the cap theorem, which states that you can only have 2 of the 3 of consistency, availability, and partition tolerance. And because a single machine failure represents a partition, partition meaning network partition, but a single machine failure is indistinguishable from a network partition, so you won't find a valid distributed system that's CA. They're all CP or AP. And I'll evaluate where each implementation lands on that distributed system cap compromise. Then I'll talk about whether the implementation has solved the new enemy problem the way Zanzibar has, or through any other method that we can surmise based on what we know. And finally, I'm going to rate the developer experience. Google has the benefit of being able to require people within Google to use Zanzibar. Outside of Google, you'll find that a lot more services have to attract people to using the service. So there is room for improvement in the developer user experience versus what's shown in the paper. So the first implementation, Zanzibar itself. It's the service that started it all. It was the cause for creating the paper. In terms of deviations from the paper, there are rumors of some unpublished work around improving the dev UX. I'm not privy to any of the details there, but we can assume that the service has not stood still since the paper was published in 2019. Zanzibar, the service also relies on a bunch of Google internal infrastructure technologies. Gaia, that identity service that we talked about. Spanner, the atomic clock-based consistent global database. Borg, Google's way of scheduling jobs within their clusters. Slicer, that consistent hash algorithm that's tied to Borg. So there's a lot of really cool services, foundational services that Zanzibar is built on top of. So Zanzibar is really standing on the shoulders of giants within Google. So the Zanzibar scorecard. How faithful is it to the paper? Well, I'd say it's probably pretty high, considering that the paper was based on it. Again, there have been potentially some improvements or changes since then, but I would imagine it's still pretty much the same internally. How scalable is it? 10 million requests per second across 10,000 servers. Super scalable. What is the cap compromise that they've made? Well, because it's built on top of a consistent data store, and if that data store goes away, it's actually CP, right? So they will choose not to give an answer versus giving a wrong answer. But they mitigate the availability aspect in some sense through the use of Zookies and bounded stacks. Did they solve the new enemy problem? Yes, they solved it with Zookies. And how's the dev UX? Based on what's written in the paper, I would say that it's average. Based on what's potentially, the rumors of improvements, it's actually unknown. It could be great inside Google for all I know. Next implementation I want to talk about is Orikeeto. Orikeeto gets a lot of press inside Hacker News or around various communities by virtue of being open source. As of recently, Orikeeto does not support user set rewrites or Zookies, as far as I can tell. And it has also not yet implemented most of the scaling strategies from the implementation section of the paper. So Orikeeto is more of a Zanzibar API implementation than a Zanzibar the service implementation. So how does it do on the scorecard? Paper faithfulness, the APIs, it seems like they've really gone to pretty good lengths to replicate the APIs. So I'm giving it a medium. Only a medium because they don't have Zookies and user set rewrites, which are actually foundational and very important to giving the right answers. Orikeeto does all of its persistence to a database or to another data store that's implemented behind a driver interface. As of right now, with a database backend, I would rate the scalability as low, especially considering that they haven't implemented most of the distributed system scaling techniques. Where is Orikeeto on the cap compromise? Without being a distributed system, they don't have to make a cap compromise. Or put another way, they are sacrificing both partition tolerance and availability for the sake of consistency. Is the new enemy problem solved? Well, if it's not a consistent system or not a distributed system, and it's always going back to the source of truth of replication or relation tuples, then yeah, it's solved. You can't serve stale data if you always only read the freshest data. And how is the dev UX? Based on the fact that you can't do user set rewrites, and they have made some sort of puzzling changes to even the API explained in the paper, I would have to rate the dev UX as poor. There's another hosted service similar to Zanzibar within Google and our own service Authzed called Sandcastle. This is a new service that Auth0 is currently developing. It's in private beta. There is almost no information about the implementation. They do have a playground that you can play with online to see how some of the APIs work. From my playing with the playground and reading of the documentation, it doesn't appear to support cookies, but it does support relation rewrites. We don't know a lot about Sandcastle, so the scorecard is going to be a little confusing. Paper faithfulness. Based on the namespace definition language that they've published, I'd say it's probably high. It seems like they have been reading the paper with a careful eye toward the implementation. Scalability and the distributed systems compromises, we don't know. We don't know anything about how it's implemented. Have they solved the new enemy problem? Without knowing whether they're taking a strategy similar to Ori Keto and just always returning consistent answers, we actually don't know that either. All I know is that I can't find cookies in the API. And how is the developer user experience? I'd say it's really similar to the user experience of using Zanzibar itself. Next implementation that there's data about is the Airbnb Himeji. I referenced their cache hit ratio earlier. Some of the deviations that they've made are they substitute AWS Aurora for Spanner. Aurora is not a globally distributed relational database, so it's not a drop-in replacement. They do eliminate Zookies, as far as I can tell, in favor of really fast cache invalidation. So they're trying to make the staleness window as small as possible from that respect. And they have really great performance numbers. So a 95th percentile latency of 7 milliseconds, and again, 5 nines of uptime. One thing to note is one of the authors on the Himeji blog post is also one of the authors cited on the Zanzibar paper. That's Abhishek Parmar. So I'm assuming that he had some influence on the architecture. So the Himeji scorecard, paper faithfulness, seems pretty good. We don't have a lot of details. They did do some of the syntax in the blog post. Scalability, very high based on the numbers that they've published. The cap compromise, if they're doing cache invalidation the way that the blog post talks about, that would make them an AP system. So they're prioritizing availability over consistency. Without Zookies, it's hard to say whether they've solved the new enemy problem, but it seems unlikely given that it's an AP system versus CP. And the dev UX seems average as well, based on what's written in the blog post. The newest kid to the block was just published this week. This is coming out of Carta. They also are doing Zanzibar. Some of the mutations they made from the paper, they built a custom index for handling dense graphs. Without any further details, I could assume that that might be something like the Leopard cache, where they denormalize deeply nested membership, but I'm not sure. They added a tenancy concept. So Zanzibar, as written, does not have any sense of tenancy. So one client can mutate the namespace definitions and objects in the way permissions are computed for other services. One thing that's really interesting is they've invested a lot in working on attracting people to the platform. So within Carta, they have to actually attract people to use their service. So they've added things like tuple templates and visualization to make it easier to integrate with their service. They did give some performance numbers based on their cache, but not on the overall service. So the only performance numbers that we have to go on are 4.3 milliseconds for easy checks and 16.4 milliseconds for their harder checks in a dense graph. But they say that they'll write more about this in the future, so you can stay tuned to the Building Carta blog. Whole lot of unknowns on this scorecard, but based on their investment in developer user experience, I think that it's probably a really great experience to use this service inside Carta. And this brings me to the final implementation that we know about, which is our own. So the Authzed is another hosted service. It's closed source as of right now. One of the deviations that we made is we substitute CockroachDB for Spanner. CockroachDB is an open source relational database that's globally distributed, and it's inspired by the Spanner paper. So it has a lot of the same performance characteristics and APIs of Spanner. Another deviation that we made is we don't have a Gaia to tell us everything there is to know about our users. So we decoupled our notion of users from any identity provider, and users are objects just like any other. We are launching a schema definition DSL this week, which will make it much easier to write those namespace definitions, like the iTest example that I showed earlier. In our new DSL, that iTest will be about 3 lines long. I'm really excited to launch that and get it into people's hands. And the last thing to note as we move into the scorecard is this is our service, so my bias level is obviously going to be off the charts. So please take this with a mountain of salt. How is Authzed's paper faithfulness? I can say with assurance that as we've been implementing this service, we've had an eye on the paper the whole time. So our faithfulness is high. The scalability, I'm only rating at a medium right now because we just don't have the same numbers as Google and Himeji have to publish. But we have implemented most of the distributed system concepts that we talked about in section 2. Cap compromise, because we're so faithful to Zanzibar, we are also a CP system. And the new enemy problem is also solved with Zookies the same way it is in Zanzibar. Based on our requirement of having to attract people to our platform, I will also rate our dev UX as higher than the paper because we want people to really enjoy and use our service out of love and not out of being forced to. Okay, so that brings me to our conclusion. So Zanzibar is really ushering in a brand new authorization paradigm. So it's relationship-based rather than role-based or attribute-based, like things you may have seen in the past. It brings data and schema together so that we can really be aggressive about caching the decisions that we're returning to the callers. It unifies the interpretation and the calling patterns for all of the various services and all of the various apps in an application suite that might want to call into it. And obviously, Google built it with an eye towards scalability from the very beginning. So a lot of times in kind of this space or in any space with any kind of like standards bodies, you'll often end up with really elegant, really great specifications that are hard or impossible to implement scalably. So, my hat's off to Google for building such an incredibly powerful service that scales as well as it does. So that's it. Thanks for watching. I'd like to invite everybody to join us on the Zanzibar Discord, where you can talk about any of the implementations that we've talked about tonight, the paper itself, or Authzed. So you can scan the QR code or type in that link. And with that, I'll take any questions if people have them. From user Actum, are these performance metrics quorum enforced reads or single shard reads? So the metrics that we saw earlier were for safe reads. Safe reads are for ones that are already globally distributed. There is no need for quorum enforced reads in Spanner because Spanner will tell you, or Spanner will go and talk to the nodes that it needs to talk to get enough data to know that there are no transactions that will currently mutate and invalidate the data that you're talking, or the data that you're interested in. So that's not a thing like you would see in some other different like Raft or Paxos implementations. From user Refin Piece, how impactful is the cache hit rate to latency? I don't have a graph to show you, but if we think about the worst case performance of Spanner, having hundreds of milliseconds, like the tail call latency, and then we think about the idea that you sometimes have to make several round trips to Spanner to answer a single question when you're doing that kind of recursive pointer chasing, very impactful, right? If you have to make 5 or 6 round trips to Spanner, and each one of those is taking you potentially hundreds of milliseconds, then getting to a 99th percentile target of 15 milliseconds would be impossible. So it's almost entirely driven by, the performance numbers that you see are almost entirely driven by cache hit. This would actually be a great idea for a blog post in the future, because at Authzed, we can actually change our cache hit ratio by changing our quantization and develop that graph. I think that would be a great graph to share with the community. Anything else? All right. Thanks everybody for tuning in. I hope you learned something, and I hope you learned about why Zanzibar is such an awesome paper and why we dropped everything to go build a company based on it. Oh, one more second. One question more. Okay. Okay, from user Actum again. If the longest tail reads were just waiting for replication to get around to the shard they were querying, i.e. if the request timestamp was in the future relative to a particular shard they hit initially, I totally forget how to read path works for Spanner and was wondering. No, so they don't just wait around for data. They will actually go and make a cross-region read to try and resolve the data that is not present. So it just takes a really long time to go dredge up data from Europe. Okay. All right. Thanks, everybody.